Hi guys, welcome to the next section, Recommendation Systems for Predictive Analytics. Now, we move on to the first video of this section that deals with recommendation systems. Recommendation systems is a subclass of information filtering system that helps predict the rating or preference based on the rating provided by users of an item. In recent years, recommendation systems have become increasingly popular. Consequently, they're being used in many areas such as movies, music, news, books, research articles, search queries, social tags, products, collaborators, jokes, restaurants, garments, financial services, life insurance, and online dating sites. There are a couple of ways to develop recommendation engines that typically produce a list of recommendations. For example, collaborative and content-based filtering, or the personality-based approach. Using collaborative filtering approaches, an RE can be built based on a user's past behavior, where numerical ratings are given on purchased items. Sometimes, it can be developed on similar decisions made by other users who have also purchased the same items. From this figure, we get some idea of different recommendation systems. The collaborative filtering-based approach often suffers from three problems, that is, cold start, scalability, and sparsity. Let's discuss the cold start problem. Sometimes it gets stuck when a large amount of data about users is required for making more accurate recommendation systems. Next issue is the scalability. A large amount of computation power is often necessary to calculate recommendations out of a dataset with millions of users and products. The last problem is sparsity. Sparsity often happens with a crowd-sourced dataset when a huge number of items are sold on major e-commerce sites. In such a case, active users may rate only a small subset of the whole items sold, that is, even the most popular items have very few ratings. Accordingly, the user versus items matrix becomes very sparse. In other words, a large-scale sparse matrix cannot be handled. Let's move on to content-based filtering approaches. Using a content-based filtering approach, a series of discrete characteristics of an item is utilized to recommend additional items with similar properties. Sometimes it is based on a description of the item and a profile of the user's preferences. These approaches try to recommend items that are similar to those that a user liked in the past or those being used currently. A key issue with content-based filtering is whether the system is able to learn the user preferences from a user's actions regarding one content source and use them across other content types. When this type of RE is deployed, it can be used to predict items or ratings for items that the user may have an interest in. Next, we will see hybrid recommendation systems. As you have seen, there are several pros and cons of using collaborative filtering and content-based filtering approaches. Therefore, to overcome the limitations of these two approaches, the recent trend has shown that a hybrid approach can be more effective and accurate by combining collaborative filtering and content-based filtering. Sometimes, a factorization approach, such as matrix factorization and single-value decomposition, are used to make them robust. A hybrid approach can be implemented in several ways. Firstly, the content-based and collaborative-based predictions are computed separately and are later combined together, that is, a unification of these two into one model. In this approach, often FM and SVD are used extensively. Secondly, adding content-based capabilities to a collaborative-based approach, or vice versa. Again, FM and SVD are used for better prediction. Let's look at model-based collaborative filtering. Collaborative filtering methods are classified as memory-based, that is, a user-based algorithm, and model-based collaborative filtering, that is, kernel mapping recommended. In the model-based collaborative filtering technique, users and products are described by a small set of factors, also called latent factors. LFs are then used for predicting the missing entries. The alternating least squares algorithm is used to learn these latent factors. From a computational perspective, model-based collaborative filtering is commonly used in many companies, such as Netflix, for a real-time movie recommendation. We will now see the utility matrix. In hybrid recommendation systems, there are two classes of entities, users and items, for example, movies, products, and so on. Now, as a user, you might have preferences for certain items. Therefore, these preferences must be provoked out of the data about items, users, or ratings. Often, this data is represented as a utility matrix, such as user-item pair. This type of value can represent what is known about the degree of preference of that user for a particular item. The entry in the matrix, that is, table, can come from an ordered set. This table shows an example of a utility matrix. The matrix represents the ratings of users for movies on a 1 to 5 scale, 5 being the highest rating. A blank entry represents that no users have provided any ratings for those movies. HP1, HP2, and HP3 are acronyms for the movies Harry Potter 1, 2, and 3, TW for Twilight, and SW1, SW2, and SW3 for Star Wars Episodes 1, 2, and 3. The users are represented by capital letters A, B, C, and D. There are many blank entries for the user-movie pairs. This means that users have not rated these movies. In a real-life scenario, the matrix might be even sparser, that is, with the typical user rating only a tiny fraction of all available movies. Next, we will see how to develop a movie recommendation engine using an SVD algorithm for collaborative filtering, where we will see how to utilize these type of matrices. First, we will train a model using available ratings. Now, we will use the trained model to predict a missing rating in the users versus movies matrix. Then, with all the predicted ratings, a new users versus movies matrix will be constructed and saved in the form of a .pkl file. Next, we use this matrix for making a prediction of rating for particular users. Finally, we will train the k-means model to cluster related movies. Now, before we start implementing the movie recommendations engine, let's see some insights of the dataset that will be used. We will download the 1M Movie Lens dataset is downloaded from this website. I sincerely acknowledge and thank F. Maxwell Harper and Joseph A. Constan for making the dataset. There are 3 files in the dataset about movies, ratings, and users. These files contain 1,209 anonymous ratings of approximately 3,900 movies made by 6,040 Movie Lens users who joined Movie Lens in 2000. All the ratings are present in the ratings.dat file, and the format is user ID, movie ID, rating, and timestamp. Each user has rated at least 20 movies. The movies data is present in the movies.dat file, and the format is movies ID, title, and genres. And the last file is users.dat, and the format is user ID, gender, age, occupation, and zip code. Here, we will look at some explanatory descriptions of the dataset before we start developing the recommendation engine. We will start with a new Python file and rename it. First, we will define the code to ignore the warnings. Next, let's import the required libraries and packages. Now, we will load the users, ratings, and movies dataset and create a pandas data frame. The next task is to convert the categorical columns, such as movie ID, user ID, and age, to numeric using the pandas built-in _numeric function. Now, let's look at some samples from the user table. Here are the samples of user tables. Now, let's look at some information from the rating table, that is, rating dataset. These are some examples of ratings dataset. Finally, let's look at some information from the movie dataset. Here is some example from movies dataset. Now, let's look at the top 5 most rated movies. Here are the top 5 most rated movies. Let's look at the movie rating distribution using these lines of code. For this, let's use a histogram plot. Now, let's look at how the ratings are distributed across different age groups. Now, let's look at the highest rated movie with minimum 150 ratings. Now, let's look at how the movies are rated by males and females, that is, gender biasing toward movie rating. Now, let's look at how the movies are rated by males and females, that is, gender biasing toward movie rating and their difference. It's clear that in most cases, males provided higher ratings than females. Now that we have seen some information and statistics about the dataset, it's time to build our TensorFlow recommendation model. Now, let's train the model with available ratings. We will define the train.py script, which is again dependent on other scripts, but we will see the dependencies. Next, let's import the necessary packages and modules. Here, we have import the packages required for I/O operations. These are the main packages imported for training. This package defines the time epoch. Now, we will set the random seed for reproducibility. The next task is to define the training parameters. First, let's define the required data parameters such as the location of the ratings dataset, batch size, dimension of SVD, maximum epochs, and checkpoint directory. We also need some other parameters such as following soft placement if you want to allow the device soft device placement and log device placement if you want to place the logs of operations on devices. Now that we don't want to contaminate our fresh training with the old metadata, checkpoint, and model files, let's remove any such existing files. Now, let's define the checkpoint directory. TensorFlow assumes this directory already exists, so we will create it. Now, before getting the data, let's set the number of samples per batch, the dimension of the data, and the number of times the network sees all the training data. Now, let's specify devices to be used for all TensorFlow computations, that is, CPU or GPU. Now, let's read the rating file with the delimiter through the getData function. I'm assuming that you've already downloaded the necessary files and placed them in the data file directory. A sample column consists of user ID, item ID, rating, and timestamp. Then it does the purely integer location-based indexing for selection by position. After this, it splits the data into train and test, 75% for train and 25% for test. Finally, it uses the indices to separate the data and returns the data frame to be used for training. We then clip the limit of the values in an array. Given an interval, values outside the interval are clipped to the interval edges. For example, if an interval of 0, 1 is specified, values smaller than 0 become 0, and values larger than 1 become 1. We then invoke the readData method to read data from the ratings file to build a TF model. We then define the number of users in the dataset who rated the movies and number of movies in the dataset. Now, using a shuffle iterator, we generate random batches for training. This helps prevent biased results. Now, for more on this class, refer to the readers.py script. For your ease, here I've provided the source of this class. Next, we sequentially generate 1 epoch batches for testing. Now, for more on this class, we will refer to the readers.py script. For your ease, here I provided the source of this class. The model method is defined here. After that, we will define the loss function. Now, it's time to create the TensorFlow placeholders. Now that our training set and placeholders are ready to hold the batches of training values, it is time to instantiate the model. For this, we use the model method implemented and use 12 regularizations to avoid overfitting. Now, let's define the training ops. Once we have instantiated the model and training ops, we will save the model for future reuses. Now, we start training the model. This code segment carries out the training and saves the errors in the pickle file. Finally, it prints the training and validation error and the time taken. This result is abridged and only a few steps have been shown. Now, let's look at these errors graphically. From this figure, it can be observed that over time, both the training and validation errors decrease. Nevertheless, you can still try to increase the steps and see if these two values can be reduced toward better accuracy. Now, we will see inferencing the saved model. This code inference uses the saved model, and it prints the overall validation error. This method creates a user item data frame. It is used to create a trained data frame. All missing values in the user item table is filled here using the SVD trained model. It takes the rating data frame and stores all the user ratings for the respective movies. Finally, it generates a filled rating data frame, where user is the row and item is the column. Now, let's invoke this method to generate the user item table as a pandas data frame. This line will create the user versus item table for the training set and save the data frame as the user item table train.pkl file on our specified directory. Now, let's define the data parameters to be used. A number of cluster k, the maximum number of iterations, and define whether it should be used as a trained user versus item matrix. Then, the k-mean clustering function is used, which returns the movies along with their respective clusters. It takes the rating dataset, that is, ratingsdf, which is a rating data frame, and stores all the user ratings for the respective movies, k as the number of clusters, max iters as the maximum number of recommendations, and trained is a Boolean type that signifies whether to use a trained user versus movie table or untrained. Finally, it returns the list of movies or items and list of clusters. In this code, we have a silly initialization, in a sense that we use the first k points as the starting centroids. In the real world, it can be further improved. We replicate to n copies of each centroid and k copies of each point, then subtract and compute the sum of squared distances. We use argmin to select the lowest distance point. If we look at this code carefully, there's another function called bucketMean. It takes the data points, the best centroids, and the number of tentative clusters, that is, k, and computes the mean to be used in the cluster computation. Once we have trained our k-means model, the next task is to visualize these clusters representing similar movies. This is why we have applied PCA to reduce the dimensionality without sacrificing the quality much. For movie rating prediction by users, I've defined a function called prediction. It takes the simple input about users and items, that is, movies, then creates TensorFlow placeholders from the graph by name. It then evaluates these tensors. We will look at how we can use this method to predict the top k movies and user rating for movies. In this code segment, clip is a user-defined function that limits the values in an array. The idea for a given interval is that values outside the interval are clipped to the interval edges. For example, if an interval of 0, 1 is specified, values smaller than 1 become 0 and values larger than 1 become 1. For our purpose, the interval is 1.05.0. Here is the implementation. Now, let's look at how we will use the prediction method for making a prediction of a rating set of movies by a user. So, this function returns user ratings for the respective user. It takes a list of numbers or number list of user IDs or just a user ID, a list of numbers or number, and a list of movie IDs or just movie ID. Finally, it returns a list of predicted movies. Let's find the top k movies. This method extracts unseen top k movies, where k is an arbitrary integer, say 10. The name of the function is top k movies that returns top k movies for the respective users. First, it takes a list of users or number, list of user IDs, and the rating data frame. It then stores all the user ratings for the respective movies. The output is a dictionary containing the user ID as a key and list of top K movies for that user as a value. In this code segment, prediction method is a user-defined function that we described previously. We will look at an example of how to predict top K movies. I have defined a function called top K similar items that computes and returns K similar movies for the respective movie. It takes a list of numbers or number, list of movie IDs, and the rating data frame, and stores all user ratings for the respective movies. It also takes K as a natural number. The value of trained can be either true or false, whether we use trained user versus movie table or untrained. Finally, it returns a list of K similar movies for the respective movie. In this code segment, the item-item correlation function is a user-defined function that computes the movie-movie correlation that is used in predicting the top K similar movies. For computing the user-user similarity, I have defined the user similarity function that returns the similarity between two users. It takes three parameters, that is, user1, user2, rating data frame, and the value of trained that can be either true or false, whether we use a trained user versus movie table or untrained. Finally, it computes the Pearson coefficient between users. In this function, we use user-user Pearson correlation function, which is a function that computes the user-user Pearson correlation.